Welcome to this problem walkthrough. In this session, we'll tackle the problem titled First Day where you have been in all the rooms. Get ready to dive into an interesting challenge where we explore a sequence of room visits guided by an array of next steps. Let's jump in. In this problem, you are given an integer array called next visit. This array has a length of n, where each index I represents a room, and the value at that index, next visit, I, tells you which room you should go to after revisiting room I. Initially, you begin in room 0 on day 0. From there, you visit exactly one room each day, following a set of rules. If it's your first time visiting a room, you move to the next room, I plus 1, as long as that room exists, that is, as long as I plus 1 is less than n. If you've already visited a room before, you follow the value in next visit, I, to determine which room to go to next. Your goal is to determine the first day when you have visited all the rooms at least once. Since the answer can be very large, you'll need to return it modulo 10⁻9 plus 7. This ensures that the result stays within a manageable range. Let's look at an example to understand the problem better. Suppose next visit is 0, 0. On day 0, you start in room 0. Since it's your first time in room 0, the rules say you move to room 1 on the next day. On day 1, you visit room 1 for the first time, so you move back to room 0 the following day. On day 2, you return to room 0. This time, since you've already visited room 0 before, you follow the value in next visit, 0, which is 0. This means you stay in room 0. At this point, you've visited all the rooms, both room 0 and room 1. So, the first day when all rooms have been visited is day 2. Now, let's examine a slightly larger example where next visit is 0, 1, 2, 0. On day 0, you start in room 0. Since it's your first time in room 0, you move to room 1 on day 1. On day 1, you visit room 1 for the first time, so you move to room 2 on day 2. On day 2, you visit room 2 for the first time and move to room 3 on day 3. On day 3, you visit room 3 for the first time and then move back to room 0 on day 4, as determined by the rules. On day 4, you return to room 0. However, this time, since you've already visited room 0 before, you follow next visit, 0, which tells you to stay in room 0. On day 5, you visit room 0 again and follow the same rule, staying in room 0. At this point, you've visited all the rooms, 0, 1, 2, and 3, therefore, the first day when all rooms have been visited is day 6. This example demonstrates how the rules work over multiple days and how the next visit array determines your movements. Keep in mind the constraints, such as the large possible value of n, which means you'll need an efficient solution. Additionally, edge cases include scenarios like n equals 1, where you're already in the only room, so the answer is 0, or cases where next visit, I, equals I for all I, which minimizes movement. These considerations will guide your approach to solving the problem efficiently. To understand this problem, we need to simulate a process where you start in room 0 on day 0 and visit rooms according to the sequence defined in the next visit array. If you encounter a room that has already been visited, the rule requires you to jump to the next smallest unvisited room instead. The challenge is to determine the first day on which all the rooms have been visited. One straightforward approach to solving this is brute force. Here, we simulate the process day by day, keeping track of which rooms have been visited and the current room we're in. On each day, we decide where to move next based on the rules. If the current room hasn't been visited yet, we mark it as visited. If it has already been visited, we find the smallest unvisited room and jump there. This continues until all rooms are marked as visited. However, this brute force approach can be highly inefficient, especially for large inputs, because we may repeatedly check many rooms for their visited status. In the worst case, this approach has a time complexity of n squared, which makes it impractical for inputs where n is very large, such as 10 to the power of 5. To address the inefficiencies of the brute force method, we turn to a dynamic programming approach. The key idea here is to define a state dp, I, which represents the first day you finish visiting room I. With this setup, we can build a recurrence relation to calculate dp, I, based on the previous states. Specifically, to reach room I, you must first complete visiting all rooms from 0 to I1. Additionally, you may need to revisit earlier rooms according to the next visit array. The recurrence relation is given as dp I equals dp I1 plus 2 plus dp I1 dp next visit I. Here, dp I1 is the day you finished visiting room I1, and dp next visit I is the day you last visited the room pointed to by next visit I. This formula allows us to account for both forward progress and the need to revisit rooms efficiently. To handle potential overflow for large values, we use modular arithmetic, typically with a modulus of 10 to the power of 9 plus 7. The time complexity of this approach is O(n), as we compute the dp array in a single pass, making it highly efficient. Compared to brute force, this method avoids redundant calculations and scales well for larger inputs. While alternative strategies, such as representing the problem as a graph and using BFS or DFS, are possible, they introduce unnecessary overhead and are less direct than this DP approach. The optimized dynamic programming approach is our chosen strategy due to its efficiency and clarity. By leveraging the recurrence relation, we eliminate redundant calculations and achieve linear time complexity, making this approach well-suited for large input sizes. While the brute force method offers simplicity in implementation, its quadratic time complexity makes it impractical for larger cases. Similarly, a graph-based approach, though viable, adds unnecessary complexity without offering significant advantages over dynamic programming. A critical insight was realizing that the problem could be reframed as a recurrence relation, allowing us to pre-compute the required days for each room. Revisits are handled elegantly by subtracting previously computed values, avoiding the need for repeated checks. In summary, the dynamic programming strategy strikes the best balance between efficiency and implementation complexity. The final time and space complexity for this solution are both O(n), ensuring it performs well even for the upper limit of input constraints. To solve this problem, we need to determine the first day when all the rooms have been visited at least once. We start in room 0 on day 0 and follow the sequence defined by the next visit array, where each room directs us to the next room we should visit. However, there are two important rules to follow. First, if we try to visit a room that we have already visited, we must wait until the next day before returning to it. Second, we continue this sequence until every room has been visited at least once. The goal is to figure out the minimum day when this happens. To achieve this, we initialize a few variables. We'll use a visited array to track whether each room has been visited, and a counter called visitedCount to monitor how many unique rooms we've visited so far. Starting in room 0 on day 0, we also define an auxiliary array called nextAvailable to store the next day each room becomes available for visitation, ensuring we follow the rules. With these in place, we simulate the process of visiting rooms step by step. The simulation begins by repeating the process until all rooms are visited. At each step, if the current room has not been visited yet, we mark it as visited and increment our visited count. We then update the next available array for the current room to ensure we cannot revisit it until the following day. After visiting the current room, we need to determine the next room to visit. This is done using the next visit array, which tells us the next room in the sequence. If the next room is not immediately available, as indicated by the next available array, we wait until the day it becomes available and update our day counter accordingly. Once the next room is ready to be visited, we move to that room and increment the day counter again, since traveling to a new room also takes 1 day. The process continues until the visited count matches the total number of rooms, at which point we can stop and return the current day as the result. The algorithm works efficiently due to key insights and data structures. First, the next available array ensures that we never revisit a room too soon, adhering to the rules while minimizing unnecessary waiting. By adjusting the day counter to the next available time, we avoid redundant checks and ensure the sequence progresses smoothly. The visited array helps us track which rooms have already been visited, while the visited count counter provides a quick way to check our progress toward visiting all rooms. These structures work together to keep the simulation efficient. For complexity, the time complexity is O(n), as each room is visited at most once, and all other operations, such as updating the arrays or waiting for a room to become available, are performed in constant time. The space complexity is also O(n), which accounts for the visited and next available arrays, making this approach optimal for the problem. To see the algorithm in action, let's walk through an example. Suppose the input array is next visit equals 0, 0, 2. On day 0, we start in room 0, mark it as visited, and move to the next room according to next visit, 0, which is room 0 again. On day 1, since room 0 is already visited, we wait until it becomes available, which is the next day, day 1. Again, we move to next visit, 0, which is room 0. On day 2, we proceed to room 1, as indicated by next visit, 0, and mark room 1 is visited. On day 3, we move to room 2, as indicated by next visit, 1, and mark it as visited. At this point, all rooms have been visited, and the process ends. The answer is day 3, as that's the first day when all rooms are visited at least once. This solution uses dynamic programming to efficiently calculate the first day on which all rooms have been visited at least once. The problem is solved iteratively, leveraging the DP array where DP, I, represents the first day you can leave room I after visiting it twice. We initialize DP 0 to 0 because on day 0, we start in room 0. For each room I from 1 to n1, we calculate DP I using the formula 2 DP I1 plus 1 DP next visit I %mod. Here's the breakdown of this formula. 1, 2 DP I1, this accounts for the time to visit all rooms up to I1 twice. 2 plus 1, this adds an extra day to visit room I for the first time. 3 DP next visit I, this subtracts the days it takes to return to the room specified by next visit I after its first visit. For %mod, this ensures the result remains within the problem's constraints, 10 to the power of 9 plus 7. The modulo operation is crucial to prevent overflow and maintain non-negative values. We also add an additional modulo operation with mod to handle potential negative values from the subtraction. The loop iterates through all rooms, computing the value of DP I step by step. Finally, the algorithm returns DP-1, which is the first day all rooms have been visited at least once. This solution is efficient with a time complexity of O, n, where n is the number of rooms, as we iterate through the next visit array once. The space complexity is also O, n, due to the DP array. This is the Java implementation for LeetCode problem number 1997, first day where you have been in all the rooms. The logic mirrors the Python solution, with type declarations and syntax adjusted for Java. The DP array is used to calculate the first day we can leave each room after visiting it twice. Java-specific adjustments include handling modulo operations explicitly to ensure non-negative results. In this problem, we need to determine the first day we visit all the rooms in a building. The key observation is that to fully visit a room, we must enter and leave it twice before moving on, following the sequence dictated by the next visit array. We'll use dynamic programming to calculate the minimum day this happens. For instance, in the example where next visit equals 0, 0, we start by initializing some constants. We define mod as 10 to the power of 9 plus 7 to handle large numbers with modulo arithmetic. The number of rooms, n, is 2, and we initialize the DP array as 0, 0, where DP, I, will store the first day we leave room I after visiting it twice. This sets up the foundation for our calculations. Now, for this example, we calculate the value of DP1, representing the first day we leave room 1 after visiting it twice. Using the formula DP I equals 2 DP I1 plus 1 DP next visit I %mod, we substitute the values. For DP1, this becomes 2 DP 0 plus 1 DP next visit 1 %mod. Since both DP 0 and DP next visit 1 are 0, we simplify to DP 1 equals 1. Updating the array, DP becomes 0, 1. Finally, since room 1 is the last room, the first day we leave room 1 after visiting all rooms is DP-1, which is 1. Thus, the output for this example is 1. Let's consider a slightly more complex example where next visit equals 0, 0, 1. We begin by initializing the constants. Here, mod remains 10 to the power of 9 plus 7, and is now 3 because there are 3 rooms, and DP is initialized to 0, 0, 0. For room 1, we calculate DP1 using the same formula. Substituting the values, DP1 equals 2 DP 0 plus 1 DP next visit 1 %mod. Since both DP 0 and DP next visit 1 are 0, this simplifies to DP 1 equals 1. Updating the DP array, it becomes 0, 1, 0. This prepares us to calculate the day we leave room 2 after visiting it twice. Next, we move to room 2 and calculate DP 2. Using the formula DP I equals 2 DP I1 plus 1 DP next visit I %mod, we substitute the values. For DP 2, this becomes 2 DP 1 plus 1 DP next visit 2 %mod. Since DP 1 is 1 and DP next visit 2 is 0, this simplifies to 2 by 1 plus 1 to 0 %mod, which is 2. Updating the DP array, it becomes 0, 1, 2. Now, the last room is room 2, and the first day we leave room 2 after visiting all rooms is DP-1, which equals 2. The output for this example is therefore 2. Now, let's look at a third example where next visit equals 0, 1, 2. The initialization remains the same. We set mod to 10 to the power of 9 plus 7, n to 3, and DP to 0, 0, 0. For room 1, we calculate DP 1 using the formula. Substituting the values, DP 1 equals 2 DP 0 plus 1 DP next visit 1 %mod. Since DP 0 is 0 and DP next visit 1 is also 0, this simplifies to DP 1 equals 1. Updating the DP array, it becomes 0, 1, 0. This sets the stage for calculating the day we leave room 2 after visiting it twice. Finally, for room 2, we compute DP 2. Using the formula DP I equals 2 DP I1 plus 1 DP next visit I %mod, we substitute the values. For DP 2, this becomes 2 DP 1 plus 1 DP next visit 2 %mod. Since DP 1 is 1 and DP next visit 2 is 0, this simplifies to 2 by 1 plus 1 to 0 %mod, which equals 3. Updating the DP array, it becomes 0, 1, 3. With room 2 being the last room, the first day we leave room 2 after visiting all rooms is DP-1, which is 3. The output for this example is therefore 3. To analyze the time complexity of our dynamic programming solution, let's break it down step by step. First, we initialize the DP array with n zeros. Since this involves assigning a value to each of the n elements, the initialization step is O(n). Next, we iterate through the rooms using a loop that runs from I equals 1 to I equals n1, giving us n1 iterations in total. During each iteration, the computation of DP I involves a few arithmetic operations, such as multiplying and subtracting values, and taking the modulus. These are all constant time operations, or O(1). Additionally, accessing values like DP I1 and DP next visit I involves direct indexing, which is also O(1). Since each iteration of the loop is O(1), and we perform this n1 times, the total cost for the loop is O(n). Finally, returning the result stored in DP-1 is an O(1) operation. When we combine all these steps, the overall time complexity of the algorithm is O(n). Now, let's evaluate the space complexity. The primary contributor to space usage in our solution is the DP array, which consists of n elements. This means the array itself requires O(n) space. Beyond the DP array, the algorithm also uses a few auxiliary variables such as mod, n, I, and intermediate values during computation like DP, I1, and DP, next visit, I. These variables take up a constant amount of space, or O(1). When we combine the space used by the DP array and these variables, the total space complexity comes out to O(n). Additionally, the time complexity remains O(n) across all cases best, average, and worst, because the loop always iterates n1 times, irrespective of the specific values in the next visit array. Similarly, the space complexity is consistently O(n), as the size of the DP array depends only on n and not on any variations in the input. Comparing this dynamic programming approach to a naive solution highlights its efficiency. A naive approach might simulate the process of visiting rooms step by step, tracking the days required to visit all rooms twice. This would involve nested iterations, as we repeatedly traverse the rooms based on the next visit array. Such an approach can lead to a time complexity of O(n) squared, in the worst case, especially when the structure of next visit causes repeated and redundant traversals. In contrast, our dynamic programming solution avoids these inefficiencies by leveraging the relationship between dp, I, and previously computed values. This eliminates redundant calculations and reduces the time complexity to O(n). The mathematical proof for this big O analysis lies in the single loop over the n rooms, where each iteration performs a constant amount of work. Similarly, the space complexity is linear, determined by the storage requirements of the dp array. Both time and space complexities scale linearly with the input size, making this solution far more optimal than the naive approach. One of the most common mistakes when solving this problem is not accounting for revisits to the same room. The next visit array might create cyclic dependencies, requiring multiple visits to some rooms before all rooms can be visited. If you don't simulate these revisits accurately, your solution will likely fail on certain test cases. Another frequent pitfall is the incorrect handling of cycles within next visit. For instance, if the sequence leads to a cycle like 2-3-2, your solution might enter an infinite loop or fail to recognize when all rooms have been visited. To avoid this, you should track which rooms have been visited and ensure proper cycle detection. Efficiency is another major concern. Directly simulating each day's room visits without optimization can quickly become too slow, particularly for large inputs like n equals 10⁵. Redundant computations need to be minimized to stay within time limits. Misinterpreting the problem constraints is another issue. Some solvers think they need to visit each room in a specific order, but the actual requirement is simply to ensure all rooms are visited at least once, regardless of order. Finally, overcomplicating the solution by using unnecessary data structures like priority queues can lead to inefficiencies. A simpler approach, such as using an array to track visits, is often more effective and less error-prone. This problem boils down to simulating a sequence of visits and determining the earliest day by which all rooms have been visited at least once. It's closely tied to problems involving cycles, graphs, or simulations. A key optimization to handle revisits is to use modular arithmetic or pre-compute values to skip redundant days in the simulation. For example, if you know a revisit is inevitable, you can calculate the next relevant day mathematically rather than iterating day by day. When preparing for interviews, it's also crucial to consider edge cases. Scenarios like having only one room, n equals 1, rooms that lead back to themselves, next visit, I equals I, or large cyclic dependencies in next visit should all be handled gracefully. During interviews, clarity is important. Be sure to explain how you handle revisits and avoid infinite loops, emphasizing the efficiency of your approach. Also, highlight the worst-case time complexity of your solution and how it handles large inputs effectively. This problem shares similarities with several other classic LeetCode problems. For instance, LeetCode 841, Keys in Rooms, also revolves around visiting all rooms, though it is modeled as a graph traversal problem. Similarly, LeetCode 207, Course Schedule, focuses on detecting cycles in a graph, which is a concept directly relevant to handling cyclic dependencies in next visit. Another related problem is LeetCode 310, Minimum Height Trees, which involves understanding tree structures and optimizing traversals, skills that can be adapted to improve the efficiency of simulations here. Lastly, LeetCode 1466, Reorder Routes to Make All Paths Lead to the City 0, is an example of a path optimization problem involving graph traversal, offering additional insights into efficient pathfinding strategies. Reviewing these problems can deepen your understanding of the underlying concepts and help you develop a more robust solution to this challenge. There are several approaches you can take to solve this problem, each with its own trade-offs. The simplest is brute force simulation, where you simulate each day's room visits and track which rooms have been visited. While this approach is straightforward, it becomes inefficient for large inputs, with a time complexity of O(n²) in the worst case. A more efficient alternative is to detect cycles in next visit and optimize the simulation. By using a visited array and leveraging techniques like modular arithmetic or memoization, you can skip redundant days and reduce the time complexity to O(n). However, this requires careful implementation to handle edge cases correctly. Another advanced approach involves mathematical analysis, where you derive a formula to calculate the day you revisit certain rooms based on constraints. While this method can be very fast for specific patterns, it tends to be less flexible and harder to generalize for all cases. Choosing the right approach depends on the problem's constraints and the trade-offs you're willing to make between simplicity and efficiency. Thank you for following along. In this session, we reviewed a fascinating problem and its solution. Remember, mastering problems like these helps build a strong foundation for tackling graph-like simulations and optimization challenges. Don't forget to like, subscribe, and keep practicing. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!